Hello again, physics friends. Today we're going to talk about the Lagrangian generalized coordinates, generalized momenta, generalized forces, and conserved quantities. And here we're going to learn about one of the real powers of the Lagrangian formalism is it kind of helps us think about forces and momenta in a more general way and blurs the distinction between, say, a torque and a force and an angular momentum and a linear momentum. We're also going to see that if a Lagrangian does not explicitly depend on a coordinate, then there's an associated conserved quantity related to that coordinate. So let's see how this all plays out. We're going to start with two very basic examples, a mass on a spring and a pendulum. And so let's start with a mass on the spring. So we've seen this system many times, right? We have a mass attached to a spring, in turn attached to the wall, and we take as our coordinate the displacement from the rest length, the equilibrium length. We'll call that x. Okay, so we can very quickly write down the kinetic energy, m over 2 x dot squared, and the potential energy, which is the spring potential, k over 2 x squared. Okay, so right away we see that the Lagrangian, which is given by t minus u, is going to depend on t and u. T only depends on a velocity and not a position, and u only depends on a position and not a velocity. So at the end of the day, this Lagrangian is going to be a function of both the position and the velocity. Okay, so when we think about the Euler-Lagrange equations, we know that we need to compute partials, right? So we're going to do d dt partial L partial velocity equals partial L partial position. So what are those partials? Let's start with the position. The partial of L with respect to x is going to be the partial of t with respect to x minus the partial of u with respect to x. But you'll notice that t does not depend on x. And since the kinetic energy does not have explicit position dependence, the partial with respect to position will be 0. Okay, so what this is saying is that the partial of the Lagrangian with respect to position is given by minus du dx. That is like a force. Okay, and in particular, in this example, du dx gives me kx. So the actual value of this for this problem is minus kx, which is the spring force. Okay, so we've learned something here. It sure looks like this term, partial L partial x, sure looks like that is a force. I'll put force in quotes with a question mark because we need to check into that a little more. Okay, but in this case, it certainly is the force. It's the spring force. How about partial with respect to the velocity? Well, that would be the partial of t with respect to the velocity minus the partial of u with respect to the velocity. But u does not depend on velocity explicitly, so that term is 0. And we're left with partial of kinetic energy. When we carry that calculation out, we're taking d dx dot of m over 2x dot squared. So we just get an mx dot here. Well, that's mass times velocity. So that's like a momentum. In fact, in this problem, it is literally the momentum of the mass. It's not something like the momentum. It is the momentum. Okay, so maybe this term, partial L partial x dot, is a momentum. And I'll put that in as a question mark for now. Well, if so, I've just moved and shrunk these guys a little bit. If that's true, that these two partials correspond to force and momentum, then what does the Euler-Lagrange equation say? Okay, it's going to say the time derivative of the momentum is equal to the force. Okay, so this is saying the time derivative of the momentum is equal to the force. Well, indeed, that's just Newton's second law. So that's kind of an interesting outcome here. Let's see if in another situation, another physical system, when we get the same result. So we're moving on now from a mass on a spring, and we're going to move towards a pendulum, a swinging pendulum. Okay, so here's our physical system. We have a ceiling not moving, pivot point in purple, rod or string of length r with a bob at the end of mass m, and the angle of the pendulum is phi. Okay, well, let's play this game out. So in order to write down the Lagrangian, we need to be able to write down T and U. The kinetic energy here is 1/2 mv squared, and now we can talk about v in 2D polar coordinates, in which case the tangential velocity, which is the only velocity because there's no radial motion, is going to be given by r phi dot. So v squared would be m over 2 r squared phi dot squared. And the potential energy, if we take the gravitational potential energy to be 0 at the ceiling, then we need to know how much below the ceiling we are. Okay, and we are a distance r times cosine phi below the ceiling. So our potential energy will be mg r cosine phi, but it's less than 0 because we're below the ceiling. So now we have an expression for our kinetic and potential energy, so we can write our Lagrangian. Okay, our Lagrangian will depend on both phi and phi dot, because t depends on phi dot and u depends on phi. Okay, so let's take some partials, right? Partial of L with respect to phi. That's partial t, partial phi, but that's 0 because t does not depend explicitly on phi, minus partial u, partial phi. The potential does depend on phi, so that second term is not 0. Okay. In this particular problem, if I take a derivative of mgr cosine phi with a minus sign, I get plus mgr sine of phi. Okay. In the past, in the previous problem, we thought this partial should be a force, right? We said minus kx, that is the force. Is it also a force here? Well, not exactly. What we're going to see is that this is a torque, which is like the rotational analog of a force, but we'll come back to that in a minute. How about the partial with respect to angular velocity? Well, that's going to have a contribution from the kinetic energy because phi dot does appear in the kinetic energy. There's no phi dot that appears in the potential though, so that term goes to 0. When I actually do that calculation out and I look at my kinetic energy, I take a partial with respect to phi dot, I get an mr squared phi dot. Okay, and in the previous example, this partial corresponded to a momentum. Is this a momentum? It turns out not exactly, but it is an angular momentum. Okay. We'll show both of those, but for now, let's just look at the main result. Okay, the main result, the Euler-Lagrange equation for phi tells us the time derivative of dl d phi dot is equal to the partial with respect to phi. Let's take for granted now this claim that the one partial is torque and the other partial is angular momentum. If that's true, then this is saying the time derivative of the angular momentum equals the torque. Okay, well, that's just Newton's second law for rotations, right? That's dl dt equals the torque. Okay, so it seems like we've kind of come full circle on this. All that's remaining then is to show that indeed these two terms are in fact the torque and angular momentum, and then we'll give a new name to these partials. Instead of calling them force and momentum, we'll call them generalized force and generalized momentum, because they don't always have units of, say, newtons and kilograms meters per second, because they could be like a angular equivalent. So to see how mr squared phi dot is equal to the angular momentum, let's look at this in this problem. We have the pendulum, we have a velocity that's tangent to the trajectory. The trajectory is a circle, so we know that the velocity is perpendicular to the radius. And so if we want to write down the angular momentum, we would say the angular momentum is r cross p, which is r cross mv phi. Okay. All right. And v phi is r phi dot. So if we look at this, we can say the magnitude of L is mag r, and then magnitude of mv phi, which is the magnitude, times the sine of theta, excuse me. And what is the sine of theta in this case? Well, it's the angle between the position vector and the velocity vector, but that angle is 90 degrees. Sine of 90 is 1. So here we have magnitude of r, the position vector. Well, that's the length of the string. mv phi is m times r phi dot. So we have the angular momentum is given by m r squared phi dot. Okay, that's exactly what we said the angular momentum was up above. All right, so this shows us that, yes, indeed, this term is the angular momentum. How do we see that this partial corresponds to the torque? All right, so for that, we can do a drawing up in the top right here. We can look at a force diagram. Okay, we don't get any torque from the tension, because the tension is parallel to the position vector, or anti-parallel to the position vector, but we will get a torque from the gravitational force. Okay, the only component of the gravitational force that provides a torque is the perpendicular component, the tangential component. Okay, and that is Fg times the sine of phi. So if we were to write down the torque, we would say the torque is r cross Fg, because there's no torque from the tension, and that is equal to, in magnitude anyway, r times mg times the sine of phi, which is exactly what we thought that was the torque before. Okay, so what we've shown is, for a linear system mass on a spring, the partial of the Lagrangian with respect to x is the force, and the partial of Lagrangian with respect to the velocity is the momentum. And therefore, the Euler-Lagrange equation says the time derivative of momentum is force. Check. Is the same thing true in all systems? No, not exactly, but it's loosely equivalent. Here, in an angular system like a pendulum, we found that one partial corresponds to the torque and the other partial corresponds to the angular momentum, so that the Euler-Lagrange equation is telling us that the time derivative of the angular momentum is equal to the torque. Okay, so how do we phrase this in general then? So here's how we're going to say it. when you have a Lagrangian, it can depend on a generalized coordinate and a generalized velocity, q and q dot. We're going to call the partial with respect to the generalized velocity, we'll call that the generalized momentum. Okay, and we'll give it the name P sub q, meaning the momentum associated with the coordinate q. Okay, and we will call the partial with respect to the coordinate itself, we'll call that the generalized force. Okay, and maybe we could call that F sub q. Okay, so in the cases that we've seen, we had a generalized momentum for the spring mass system that was the momentum, and we've had a generalized momentum for the pendulum system that was the angular momentum. Okay. All right, so the subsequent thing that we want to say is that the Euler-Lagrange equation tells us that the time derivative of the generalized momentum is equal to the generalized force. Okay, in other words, the time derivative of a momentum associated with Q is equal to the force associated with Q. So we might call this a generalized Newton's second law. And I think this is a really nice unification in physics between the angular regime and the linear regime, and then also for some generalized coordinates that is neither an angle nor a Cartesian coordinate. You're going to have an associated generalized momentum for that coordinate and a generalized force as well. I have one more thing I want to say about this, right, which is we know that if there's no force on a system, then the momentum of that system is conserved. ddt of that momentum is 0. Now, if the generalized force is a partial of Lagrangian with respect to coordinate, what that tells us is if the Lagrangian does not contain that coordinate, then the associated force will be 0 and the associated momentum will be conserved. So I want to talk through that one idea that if the Lagrangian does not explicitly depend on a coordinate, then there's going to be an associated conserved quantity. Let's take a look. So now we're focusing on the second item for today, ignorable coordinates and conserved quantities. And here, ignorable, I'll put in quotes, because that is the term that is used to describe coordinates that do not appear explicitly in the Lagrangian, okay? So let's say you have a Lagrangian, and in general that Lagrangian could depend on a coordinate and the velocity, but let's say for some reason, and we'll show an example in a minute, the Lagrangian only depends on q dot, but not q, okay? If that's true, then we know that the partial derivative of that Lagrangian with respect to the coordinate q will be 0, and that tells us that the Euler-Lagrange equation for q will be the time derivative of partial with respect to q dot is equal to partial with respect to q, but that term is 0. That implies that the time derivative of some quantity is 0, which then implies that that quantity is constant or conserved. But this quantity, remember, is the generalized momentum. So this tells us that the associated momentum is constant. If a coordinate does not appear in the Lagrangian, then the associated momentum for that coordinate is constant. And anytime we know that anytime we have a constant of the motion, that's a useful tool for problem solving. So let's do an example in which we can see that we're going to have a conserved quantity. Okay, so here's the setup. We're talking about projectile motion. We have the ground, and we have a mass thrown or shot at some angle, so it has a velocity in the vertical and the horizontal directions. We have gravity pointing down. And I've defined a coordinate system where x is the horizontal direction, z is the vertical direction, and y is into the page. Okay, so we have really, I guess, a 3D problem in general, but we have one constraint. And that constraint is y equals 0. There's no motion in the y direction, so y dot is 0, y double dot is 0. So we just need 2 degrees of freedom, or we have 2 degrees of freedom, so we need 2 generalized coordinates. Okay, and the motion is in the xz plane, so it seems sensible to use for our coordinates x and z for our generalized coordinates. Okay, so let's proceed with that. We can write down t as m over 2 x dot squared plus z dot squared, and we can write down u, which is mg times the height. The height is z, so our potential is mgz. So now we construct the Lagrangian. It's t minus u, m over 2 x dot squared plus z dot squared minus mgz. And let's take stock now of our Lagrangian. It involves z, x dot, and z dot, but x does not appear. Okay, so we can make that explicit by saying, in general, the Lagrangian could have depended on x and z and x dot and z dot, but it does not, in fact, depend on x. So immediately, we know that the partial of L with respect to x will be 0, so we would expect the associated momentum to be constant. Okay, so let's just play this out. And of course, our intuition, like we know this problem, we know that the velocity of this ball in the x direction is constant. It does have a constant momentum in the x direction, even though the momentum in the z direction is changing due to this potential. Okay, but let's play it out. All right, so partial of L with respect to x is indeed 0. Partial of L with respect to x dot has a contribution only here, and we get mx dot. Okay. Remember, this is the generalized force, and this is the generalized momentum. The Euler-Lagrange equation for x tells us the time derivative of the momentum is equal to the force. Okay. We put in the values that we have for this problem. We find ddt of mx dot is 0. That's saying the time derivative of mv is 0. In other words, the time derivative of the momentum in the x direction is 0. And we knew that because x is an ignorable coordinate. X did not appear explicitly in the Lagrangian. There's no x present in the Lagrangian. Therefore, the partial with respect to x is 0. Therefore, px, the momentum in the x direction, is conserved. Okay, so this is a very powerful tool, because all you have to do now is you write down the Lagrangian, and if you just notice by looking that a given coordinate is missing, that tells you that the momentum associated with that coordinate is constant without doing any math. It's very, very powerful. Notice also that the y-coordinate does not appear in our Lagrangian. Okay, so that tells us that the y momentum is also conserved. That's a true statement, but it's not so interesting because there's no motion in the y direction. So yes, the momentum in the y direction is conserved. It's 0, and it will always be 0. But the x momentum is non-zero, but the Lagrangian's format, meaning that the absence of x in the Lagrangian, tells us that this particle will march along at constant speed in the x direction. Okay, that's all I wanted to do. I wanted to kind of talk about generalized force and momentum, what that means in terms of the Lagrangian. We saw that the partial with respect to the coordinate corresponds to an associated force. We call that the generalized force. And we saw that the partial with respect to the velocity corresponds to the generalized momentum. We then see that the Euler-Lagrange equation is kind of a generalized Newton's second law, which tells us the time derivative of a momentum is equal to a force in generalized terms. And then we found that if a coordinate is absent from the Lagrangian, then that generalized force is 0 and the associated momentum is conserved. Good. Hopefully this has given you some intuition into the connections between Newton's second law and Euler-Lagrange equations. And we'll be practicing this a lot more, but until next time, take care and be well.